Hello, everyone. Welcome to the launch of our exciting new talk series on privacy-enhancing technologies. We are thrilled to bring together leading researchers and experts in this critical field. Today, we have our inaugural speaker, our first speaker, Professor Salil Vadhan from Harvard University. Professor Vadhan will present to us his journey from the theory of differential privacy to practice and back. His work has deeply advanced our understanding of the theory of differential privacy, while simultaneously pushing for its adoption in practice through the OpenDP project. Following Professor Vadhan presentation, there will be a Q&A session chaired by Andrew. So yes, thank you, Salil, for being today with us, and you have the virtual floor.
Thank you, Tudor and Ivy and Andrew for having me, and a virtual hello to everyone who's in the audience. So it's great to be here. So I understand that part of the point of this lecture series is to try to reach people who are early in their journey as researchers or practitioners in privacy-enhancing technologies, and so I thought it would be useful to kind of give that similar context for myself and where I started out and how I got into this field. So when I did my PhD 25 years ago. Surprisingly long ago. My focus was in the interface of complexity theory and the foundations of cryptography. My PhD thesis was on the complexity theory of zero-knowledge proofs. And for those who don't know, what complexity theory is the subfield of theoretical computer science that tries to understand the limitations of efficient algorithms and try to classify problems that we want to solve with computers according to how difficult they are and what resources like randomness or time or memory make problems easier or harder to solve. And this is, of course, the basis for much of modern cryptography, which is based on our understanding of which problems are intractable, difficult to solve, and we want to design then encryption algorithms and other protocols that are intractable to break. My perspective at that time, my starting point was really on the basic science, trying to understand things about the capabilities and limitations of computation. And even though, of course, a lot of the questions were inspired by things that come up in practice, my own interest and my work was very far from practice. It was really on advancing our foundational understanding. And that continued for a while. And late in my PhD and my postdoc, I added a focus on another area at the interface of complexity and cryptography, the theory of pseudo-randomness. And really a driver for me there, although there's many applications of pseudo-randomness in real-life cryptography, was really on a complexity theoretic question of understanding the power of randomized algorithms. And it wasn't until my time as junior faculty where I started to really get interested in data privacy, thanks to an interdisciplinary center that we have at Harvard, the Center for Research on Computation and Society, that exposed me to the data privacy challenges that society was facing more broadly, and that people in other and got me to interact with people in other disciplines that were thinking deeply about those questions. And those were the years in which differential privacy was just starting to emerge from the theoretical computer science literature, and heard some early presentations on it that intrigued me. And so what differential privacy aims to do, I'll be kind of very quick in this portion, guessing that a lot of the audience has some familiarity, is to enable statistical analysis of sensitive data while ensuring that information about specific individuals is protected in a very strong sense. So learn about a population, so get signal about the population, but hide information about individuals. And so this includes when you're training machine learning models, publishing statistical tables, releasing synthetic data sets, differential privacy is applicable. Also query systems where analysts may come in and ask custom questions of their choice. So you imagine like a web interface to a sensitive data set, like for education data or census data or genomic data or search trends. And the reason differential privacy is needed is that it's now fairly well understood with many demonstrations that the traditional, more ad hoc methods for trying to protect privacy in sensitive data sets are quite ineffective and often are subject to quite severe privacy attacks, things like re-identification attacks that many of you may have heard of, but even attacks on aggregate statistics, things like what are called database reconstruction or membership inference attacks. And I won't go through these in detail, but some very sort of visceral examples happen with machine learning models where even earlier generations of ChatGPT, when fed with carefully constructed prompts, reveal specific items from their training data. So they're kind of intended to learn a general model of language and learn general facts, but they inadvertently memorize some of the specific training data, which can be very sensitive personal information. And the same holds for image models as well. And this problem has only gotten worse as the models have gotten bigger and thus more prone to memorization. Okay, so that's the motivation for differential privacy. And then what it aims to do is protect individual level data in a very strong sense, kind of against whatever kind of computational strategy an attacker follows, whatever auxiliary data, background information an attacker brings, even about a specific individual they want to attack. And so what differential privacy requires that an attacker interacting with the system shouldn't be able to tell even whether a specific individual's data is in the data set or not, or whether that data was replaced by kind of arbitrary other values. And again, I don't want to get too technical in this is just an example. The way in which differential privacy is typically achieved is by introducing carefully calibrated amounts of random noise into the way we answer and compute statistics on the data, or construct our statistical releases, or train our machine learning models. So as a very simple example, if you're asking a question about what fraction of the data set, your population, has some traits, a way you can achieve differential privacy is to compute the exact answer and add a small amount of random noise that's enough to obscure the effect of each individual while still allowing the signal about the population to come through. And then the way the guarantee is formalized is by saying that what the attacker sees, what you release, has approximately the same distribution. It's kind of randomized from the noise. It has approximately the same distribution regardless of whether you were in the data set or not. All right, so if we consider any two data sets that differ on one individual's data, an attacker seeing the result won't be able to tell the difference. Right, and this is just for answering one queries, but then differential privacy also allows you to reason about what happens when you try to answer many queries with differential privacy and how the privacy loss degrades. All right, and so differential privacy is a quantitative theory giving quantitative measures of how much loss, information leakage, a loss to privacy there is about individuals with each query you answer, or with what a system guarantees overall with its privacy loss budget. And this can be measured in a number of ways. Many of you may have seen the basic definition of differential privacy, which is shown here, where there's a privacy loss parameter epsilon that's governing the leakage of information and how close the distributions are, whether you're in the data set or not on any two kind of adjacent data sets. And then you may have heard terms like approximate differential privacy, concentrated differential privacy, Renyi differential privacy, FDP. These are all more sophisticated ways of getting more information about the privacy loss so we can reason about it more accurately, and in particular have a better understanding of how privacy loss degrades when you're answering more queries with differential privacy. The formal definitions won't matter for this talk. Okay. So when I started working on differential privacy, there was a thing that got my foot in the door was a really amazing result by Blum, Liggett, and Roth that said that really powerful synthetic data generation was possible in principle with differential privacy. And if you have a data set, say with categorical data like shown here, and provided the number of attributes is somewhat smaller than the number of people in your data set, the number of records, then you can generate a synthetic data set that is differentially private, meaning no one individual in the original data set has a noticeable, a detectable influence on what you produce in your synthetic data set. So this is not just de-identifying your original data. There's no one-to-one correspondence between individuals in the original data set and the output. And yet, very rich statistical properties of the original data are preserved. In particular, for every subset of attributes like sex, blood type, disease status, every possible combination is simultaneously preserved up to say, 1 plus or minus 1% in the synthetic data set. So this seemed really amazing from a utility point of view and the fact that it's compatible with differential privacy. But the severe limitation of this method was that the computation time it required was exponential in the number of attributes. And so if you think of a data set with 50 attributes or 100 attributes, which is quite common, this becomes completely infeasible to actually carry out. And so bringing my kind of complexity theory hat on, this was a very natural way kind of question for me to start looking at, is to understand, because complexity theory is about understanding what is possible with efficient algorithms and what's not. And one of our early results was to give strong evidence that for this kind of very general purpose synthetic data generation with differential privacy, it actually requires exponential computing time if you believe that cryptography is possible, okay, which is kind of widely believed under standard assumptions for cryptography. And this was the flavor of much of my early work on differential privacy, was really sort of like delineating the limits between what's possible and what's impossible, both in terms of computational terms, as well as in the privacy utility trade-off and kind of the statistical complexity, how much data you need to do differential privacy effectively. And so this is, one example of how differential privacy has really turned out to be a gold mine from a research point of view. I came in as a complexity theorist and found many opportunities to apply my toolkit and many interesting questions that arise by looking at the challenges that differential privacy was encountering. And the same has been true for many other theoretical and even non-theoretical areas of research in computer science, mathematics, statistics, and so on. At the same time, it also addresses a very urgent societal need. And so there also is the appeal of actually trying to bring the possibility of differential privacy to practice. And that, this is a good way to transition into kind of what my more recent, and particularly the last decade of work on differential privacy has been driven by. So this all began with the Privacy Tools project that we began at Harvard in 2012, which was an interdisciplinary project bringing together computer scientists together with legal scholars who were thinking about privacy, quantitative social scientists who were thinking about how to grapple with the sensitive data sets that they were getting their hands on and the expectation that they share those data with other researchers, but without having the tools to do so safely, with the increasing knowledge that kind of traditional de-identification is ineffective, statistics and others. And this project is really what got me interested in, turned my interest not just from the basic science questions of understanding what's possible and impossible, but I was really drawn to the the problems that differential privacy was trying to solve, the problems on the ground of sharing data. It seemed like there was a lot of societal value that could come from the safer sharing of these sensitive data sets. And differential privacy seemed perfectly designed to try to address those problems. And so we began this privacy tools project to kind of understand, can we do this? Can we bring differential privacy to practice? How is the way that we're mathematically modeling privacy in this field relate to the way that, for example, legal scholars are thinking about privacy? And can it really solve the problems that practicing researchers were facing with their data sets? And coming out of the Privacy Tools project led us to launch OpenDP about 5 years ago, this open source software project, which is really designed at being a community effort to build trustworthy open source software for statistical analysis of sensitive data, using the protections of differential privacy, and really aimed at trying to, again, open up sensitive data sets for research and exploration in the public interest. And some of the, while there's an increasing amount of differential privacy software out there, the three of the features that we're kind of really trying to highlight in OpenDP, one is trustworthiness of kind of really trying to be confident that we've implemented differential privacy correctly and it's providing the guarantees that it promises. Flexibility to adapt to new applications rather than building a bespoke system for one particular application that's hard to adapt to others. And finally, I got really excited about building a community project inspired very much by what was happening with OpenMined, where it's not just trusting one organization to produce differential privacy software, really engaging the community of people in industry, academia, government, who are working both on the science and the practice of differential privacy together to try to build software that's as valuable as possible and bring it to really positive applications. So we're grateful to all of the organizations that have provided us with support and those that we're collaborating with. I'm joined in leading OpenDP with Gary King, who's a quantitative political scientist, along with a great team of developers, researchers, and staff, and benefit a lot from contributions from interns and fellows, like Tudor has been working with us, doing some wonderful work. And we're also grateful to our advisory board of thought leaders in this space. And I want to just try to get to some of the research challenges that come out of working on OpenDP. So the story I'm trying to tell us here is starting from the theory of differential privacy. That's my starting point. I've told the story of how I kind of got to practice, and I want to lead to how this work on practice, again, gives back to the science and theory by raising interesting research questions for us to work on. So to do that, I want to talk a little briefly about the OpenDP software. It's the OpenDP ecosystem is kind of broken into two parts here. And the part I want to focus on is the part that we call the OpenDP Commons, which is the really community-owned, community-governed portion of the software. And the core of that is the OpenDP library that I'll talk about in more detail. But for context, I want to mention that there's also kind of end-to-end systems that are part of the OpenDP ecosystem, some that are kind of part of the community portion of the project, the OpenDP Commons, and others that are products that are built in partnership with another organization, like the Smart Noise Suite that we worked on together with Microsoft. And you can see all the software in the OpenDP repository, and some recent use cases that OpenDP has been brought to, a really exciting project on understanding the digital divide by Microsoft, working with economists and business researchers to understand the divide between different portions of the population and different socioeconomic groups in what kinds of digital applications they make use of. We have prototypes that we're working on together with the Swiss Federal Statistical Office. We're excited that OpenMined has integrated OpenDP into PySift and being used in pilots in a number of national statistical offices around the world. And Oblivious has an integration of OpenDP in the anti-granular platform that can be used to run contests around privacy-enhancing technologies. So just to anyone out there who's using OpenDP or is interested in using OpenDP, we want to know and we want to be in touch with you because we really want the work we're doing on the project to be driven by the needs and applications that you all are confronting. All right, so diving into the library, the OpenDP library is implemented in Rust for performance, but you can use it from Python and R. There are bindings for both of those. And I mentioned trustworthiness as one of the key features that we're seeking to achieve with the OpenDP library. It's one of its main selling points. And the way this is happening, the vision for this is that, how do you build trustworthy software that's taking in contributions from an international community around the world? How are you sure those implementations are correct and not inadvertently introducing vulnerabilities into the library as we take in those contributions? So the idea is that we have a vetting process for contributions to the library, and attached to each core component of the library, there is actually a mathematical proof attached to the code that is proving that it satisfies the claimed properties, that it meets the specification that's needed for it to interoperate and for the library as a whole to provide the differential privacy properties that we want. Okay, and there's a privacy proof review board. Tutor is sitting on that board that's now in operation that is reviewing these proofs. And so we're looking for people to write proofs for more components of the library so they can undergo review by the Privacy Proof Review Board. All right, so now let me dive into a little more detail. So the OpenDP programming framework is the specification under which the components are written in the library. And again, here we're seeking generality and trustworthiness. And another thing that I will, if time permits, get to is support for interaction kind of as what's called a first-class citizen in the library and in the programming framework. All right, and so the idea is that we have the library has components or constructors for components that are known as measurements and transformations, or measurements you can think of as mechanisms in the more common vernacular of differential privacy. These are the basic components that can then be combined together with other elements of the library that we call combinators to build complex differentially private programs, to do complicated analyses. And the point of the modular framework is that if we have proofs for each of the components, the privacy proof for the complex DP program that you build out of them is, in a sense, automatically derived. Okay, and so you can mix and match components to do lots of customized analyses with the OpenDP library. Okay, so let me tell you a little bit about what these components are. Measurements are what we, again, as I said, typically call a differentially private mechanism. Okay, and recall, definition of differential privacy says if I have two data sets that are close in the sense that they differ on one individual's data, then the output distributions should be indistinguishable. They should be close as probability distributions, what I get with your data in the data set or your data not in the data set. And the OpenDP notion of a measurement is a generalization of this concept to allow essentially arbitrary ways of defining what we mean by close, both on the input as well as on the output distributions. So for the outputs, oops, I've lost my, apologies, lost my buttons to transition the slides, got it back. So on the output distributions, you can pick, for example, any of the different flavors of differential privacy that I mentioned earlier about pure, approximate, concentrated, Rennie, FDP. And similarly on the input. And then what transformations do, they kind of allow you to reason about what happens in a data processing pipeline. So I start with some data set like on the left here, and let's think about the task of computing a differentially private sum. Okay, so of some query or predicate on the data set. So if I start with two data sets that are adjacent, differ on one person's data, and now I consider the first step, the first transformation, which is applying some mapper function Q to each record in the data set. So this is, for example, if I want to know how many individuals in the data set live in zip code 02134, it's the zip code I'm in right now, this Q would just be replacing each record with a 0 or a 1 according to whether they're in that zip code. All right. And now to reason about the privacy properties, we say, if my two original data sets were close to each other, adjacent, then after applying this mapper, they also are going to differ on at most one row. And now I apply a summation transformation. And to reason about the differential privacy that I'll get at the end, what we say is if I have two data sets, this 0, 1 data sets that differ on at most one row, the sums I get will differ by at most one. And then we have the noise addition mechanism, and that has the property that if I start with two sums that are close to each other, when I add noise, I'll get probability distributions that are close to each other. And all in all, this gives us the differential privacy guarantee that we wanted. Start with close data sets, you get close distributions. And transformations are abstracting kind of this reasoning that we did along the way in this data pipeline, that they are functions that map close inputs to close outputs. And you have, in OpenDP, we allow essentially any way of arbitrary ways of measuring closeness. Okay, so OpenDP is built out of these transformations and measurements, and they have these, the way that they transform input closeness to output closeness is captured by an attribute that's this stability map or privacy map. And the proofs are proving that that are attached are proving that they actually have the stability or privacy property. That if the inputs are at some input distance dn, and the map gives me a distance that's attached to the transformation, gives me a value d out, then the corresponding output should be within distance d out of each other. And through the process of verifying, trying to write proofs like this for the library components, we realized that actually the standard ways of implementing some very basic steps like the summation operator actually don't satisfy this property, even though they seem to when you reason about summation on paper. And the reason is that the way that computers do arithmetic is not a perfect reflection of idealized real number arithmetic that we write about in differential privacy research papers. Okay, and so if you're doing floating point arithmetic, there is rounding that's happening at every step of summation. And even if you're doing integer arithmetic, there's what happens when you have overflow as an example of deviation from idealized real number arithmetic. And that led us to a research paper with Silvia Cascoberta, Michael Shumate, and Connor Wagaman, where we found that virtually all differential privacy libraries out there fail to satisfy the privacy properties that are promised because they fail to account for this discrepancy between implemented arithmetic and idealized real number arithmetic. And we found ways to fix it and fixed it in the OpenDP library, right? To really have proofs that are corresponding to the way your implementations carry out arithmetic. The other research question I'll mention before wrapping up involves supporting interaction as a first-class citizen in OpenDP. That many, even though the basic definition of DP, as we usually present it, it talks about you have the data set and you produce one output from it, and you want the probability distributions to be close on adjacent data sets. But many of the useful mechanisms in DP and the ways that we want to use DP in practice is in an interactive way where an attacker may ask questions and get back answers that are also not necessarily answered independently. They may be correlated in a way that's controlled to try to minimize the amount of privacy loss accumulated over many queries. And that's captured in OpenDP by the notion of an interactive measurement, which we support as a kind of primary abstraction in the library. It models many useful things that we do in differential privacy, adaptive composition, the sparse vector technique, if you've heard of these things, privacy filters. And the research question that we realized when we implemented this in OpenDP, and again wanted to write proofs, was, do the existing composition theorems for differential privacy actually extend to interactive mechanisms? And it turned out the proofs that we had were limited in the way that they extended. So they did extend to what's called sequential composition, which is where I first interact with one mechanism, then I finish, then I start interacting with another mechanism, and then I finish, and then I go on. And so interact with mechanisms one at a time. So this is a fairly straightforward extension of our known composition theorems. But in practice, we want to be able to support what's called concurrent composition, where an analyst can ask a question to one mechanism, then ask a question to another one, then go back and ask a question to the first one, and so on, and arbitrarily interleave its interaction with different DP mechanisms. And we knew, and this is going back to my kind of training in the foundations of cryptography, that concurrent interaction is often much more subtle and dangerous than sequential interaction. And in the classic cryptography literature, there are many examples where composition that works for sequential interaction fails for concurrent interaction. All right, so I think I've already motivated concurrent composition, both in kind of software implementation. It's extremely useful, as well as when we deploy differential privacy. If we want to deploy query interfaces on the web, there's nothing to stop an attacker from interacting with multiple of them concurrently. And so in a recent series of works, we've shown, took a fair amount of effort, that most of the composition theorems we know about non-interactive differential privacy do, fortunately, extend to concurrent composition. And one by one, we tried to tackle the main forms of DP that I've mentioned earlier: pure, approximate, RENI, and FDP, as well as composition in the form of odometers and filters, where the privacy loss parameters can be adaptive as well. But there are still some open questions there. So for those who are experts, we still don't know similar results for approximate RENI DP, which would be really useful to have. And we also don't know what happens when you concurrently compose odometers with themselves. All right, so let me wrap up by just saying, encouraging you all to join the OpenDP community. We have a very kind of wide perspective on who is in the community. There are many ways to engage. You can join community working groups, attend our annual community meetings and hackathons. So come to our website, join our Slack, GitHub, mailing list, and find ways to engage. And let me close by just summarizing, hopefully convey, the differential privacy has raised kind of fascinating questions and connections for many different research areas. And the efforts to bring differential privacy to practice have raised even more. And I gave a couple of examples. And one other that I didn't really talk about is on the statistical side. Even for some very basic statistical problems like simple linear regression in just one variable, we still are getting our hands on really understanding what is the optimal way to do that with differential privacy. And so kind of look forward to the advances that will be happening in this field in the years to come, probably for many of you who are in the audience. Let me stop there. Thank you.
Thank you, Salil. That was wonderful. So, as a grad student working mostly on differential privacy, this was a very interesting and encouraging talk. So we will continue with the Q&A chaired by Andrew. Please, Andrew.
Brilliant. Yeah, Salil, thank you so much for taking the time to share those insights. I think that you have a better perspective on like the life cycle of someone entering the DP space than almost anyone in the world, to the extent that you've traversed both the theoretical and the practical, and to your extent also all the way back. So kind of up and down the path that people would jump into. So somewhat selfishly, I have one question that I'll answer before I'll get to some of the questions from the audience. Which is when you think about how would you list kind of the different entry points? I know you listed a handful of them very tangibly right at the end there, like, join Slack, play around with some of the early tutorials and tools and this kind of thing. But from kind of from the people you've interacted with, the people that are inside the OpenDP community, that are on the proofs board, and that are advisors or interns or participants or users, like, can you get a sense of like different clusters of people that you've observed in your time that seem to come to differential privacy from different directions, and kind of what if there are a few kind of general common journeys that people tend to go on, and can you kind of characterize maybe what some of the valleys of that journey kind of look like for 2 or 3 cases?
Yeah, great. So I think there's a fair number that follow a journey that's similar to mine, but coming from a different subfield of computer science. So in the early days, most of the people coming into differential privacy were probably theoretical computer scientists, because that's the subfield of computer science at which it originated. But pretty quickly, it got picked up by other subfields: databases, programming languages, computer security, systems researchers, then people in statistics, and coming from different perspectives in statistics, people in biomedical informatics. And the nice thing about differential privacy is that it has provided opportunities for kind of each of these different people coming from each of these different groups to bring their unique skill set and their interests and their background, and find ways to apply it to differential privacy, and apply differential privacy to the questions from the area that they're coming from. And so in general, that's something that I think of as really important in finding yourself and building your momentum as a researcher, is like figuring out what's that unique combination that you're bringing in, that may be different than what other people do. And at first that's a little frightening. Oh, what I'm coming in as someone with a different skill set than what most of the people working in this area. But actually, that's a huge asset, because you're bringing in you're creating an opportunity to do new things and have new intuitions that people who are currently working in the field don't. Of course, you need to get over some of that hurdle of learning the area and understanding what people who are speaking a different language, and that takes time and effort. But try to stay sort of confident that you'll find a way to apply your unique skill set. So that's from academia. There's also a set of people now that are coming to differential privacy from the applications, people who are in industry, or developers in industry, or statisticians at a statistical office, who are coming to differential privacy because of the applications that their organization is facing. And I think it's probably a very similar story, that they have also their own unique skill set and experiences that they can then bring to their work on differential privacy.
That's brilliant. So it almost sounds like the common thread is differential privacy likes to be mixed with other things, I suppose. And so step one is to know what ingredients you might be bringing as a professional that can mix well with differential privacy. And then step two, you said, was sort of familiarizing yourself with the language and the basic literature and main concepts. And it sounds like the OpenDP kind of website tutorial, Slack, this kind of thing is like a good place to get started for that kind of thing.
Yeah, OpenDP, the OpenMined community as well, I would say is, I would say 5 years ago, we were probably in a pretty poor place regarding bringing new people in terms of it was like a pretty high barrier to cross. That things were really written for specialists. Most of the materials out there, but I think the situation has really improved, and now there are also these communities where you can ask questions. Lots of tutorials out there. Things that are much more hands-on, where you get to work with code and work through tutorials that are in notebooks. So hopefully that barrier to entry is getting lower and lower.
Cool. All right, I'll ask one more question along this line of threads, and then I'll get to the flurry of questions from folks in the audience. And that is like, if you were a new person interested in differential privacy, what would you suggest would be like the first goal that they should have that it would kind of help accomplish these two kind of steps that you just mentioned a second ago? Is it and if you have a couple different ideas, feel free to list a couple different ideas too. But yeah, like what would be like the first milestone that would be worth kind of chasing?
Yeah, that's a good question. I mean, I'm a big fan of start small, and start again with the things that are maybe closest to the expertise that you're bringing in. But try to like pick a really sort of well-contained problem to work on, whether that's a kind of a potential application or it's a research question, and use that as a stepping stone. And again, in the story I told, I really started with questions in differential privacy that were very much in the wheelhouse of the expertise that I was bringing in as a new person to that area. And with time, I started to be able to do some of the other kinds of things that people in differential privacy were working on, of designing new methods and all of that. Whereas what I started out with was kind of understanding limitations and what things were hard, because that's the skill I had coming in.
Brilliant, very helpful. Love that. All right, enough of the questions that I'm putting in. So first one I've got here is from Beliogi, who asks, can differential privacy be effectively used in combination with other privacy preserving techniques like homomorphic encryption or secure multi-party computation?
Yes, absolutely. Great question. And it's something I should have included explicitly in the talk. So it's very complementary. Sometimes the phrases that are used is that differential privacy is a output privacy technology or methodology. It's protecting the results of making sure that the results of computations are not too disclosive about individuals. The other technologies you mentioned, secure multi-party computation, whether done through a cryptographic protocol or done in a trusted execution environment or fully homomorphic encryption, these are often called input privacy techniques. And really what they protect is they protect the privacy of the inputs in the process of the computation itself. It allows you to carry out a computation, say, between different parties that don't trust each other, and so that the process of the computation doesn't reveal more than the output. Okay, but then you still need something like differential privacy to ensure that the output itself is not too disclosive. And so they really can be used in conjunction. There are sometimes technical challenges in doing so efficiently and effectively, but there's been continual progress on that, and I think a number of examples that are out there in practice, particularly with DP in trusted execution environments.
Cool. So if someone, that was gonna be my next question, which is like, if someone wanted to get their hands dirty with a combination of these two things, what's the best jumping off platform? What's the best, do you have a favorite tutorial or location or something like this you'd go check out?
Maybe I'll bounce that question right back to you, Andrew, because I think you all in OpenMined have a bigger focus on the integration of different privacy enhancing technologies than we do in OpenDP. And so I would normally point folks to OpenMined as a place to go.
Awesome. Well, that sounds great. In that case, I'll point two people to the PySafe repository, and we can go to the next question. Here's an interesting one. So Duarte asks, what do you think about machine unlearning, and do you consider it a promising tool in the pet world? They think that overlaps with differential privacy, but do you have any opinions on this concept?
Oh,
I guess unlearning is kind of like what happens if you didn't have differential privacy early enough, I think, and you're trying to fix it after the fact. But I don't know if there's any interesting ties you'd like to point out.
yeah, so I really only know kind of about machine learning at a fairly superficial level, right? And somehow training, with differential privacy, which is the way I would typically recommend to try to go if we can, if you can get it to work effectively enough, sort of has the property that you're automatically unlearned in that what the model that you get is as if any one individual's data were removed from the training set. And so from my admittedly distant understanding, I think of a lot of the work on machine unlearning is kind of is a solution for the fact that we don't yet have differentially private machine learning being done pervasively in practice, and would love for us to be able to reach that point.
Brilliant. Bart has asked, how can DP be leveraged to facilitate audits or support more comprehensive third-party evaluations of state-of-the-art models developed by Frontier AI Labs?
Great, interesting question.
So I think I can probably help frame that question a little bit too, if that's helpful. So we've done a fair amount of this type of work, which might be also why there's a lot of interest in it. There's kind of two styles. One tends to be accessing data at one organization, so like training data, user logs, AI models, this kind of stuff, where you might be protecting data of like a large number of users or a large number of data providers or something, or the vector space of parameters or something like this. And then there's like kind of a second scenario, which is more like I'm a join scenario, not unlike what's encountered in stats agencies that you'd be familiar with, where you're doing some type of join across data at multiple different locations to facilitate some type of evaluation. Typically, it's like a user log and then like some user health data if you wanted to know whether like a model is contributing to some health outcome or something like that that might be in a different location. So yeah,
great. And the auditing aspect, maybe do you want to like?
Yeah, so the audits are typically I guess there's a few different forms of audits. Some are speculative, where it's like I'm trying to test whether a model is likely to exhibit some type of behavior. Privacy enhancing technologies are typically used more in like a intellectual property protection context there, where it's like I have some framing in my head of like I don't the vector space of AI models is probably the most common one, where like no one really cares too much about the privacy of an individual parameter being disclosed, but like the overall kind of there's some sort of link between the IP and value and intelligence in an AI model and like kind of some sort of notion of group differential privacy. It's still very vague, but I think some folks reach for differential privacy in that context to try to prevent reconstruction attacks of the model. And then the other kind is audits that are non-speculative audits of the actual user log itself, which is really about what users did. This could be descriptive statistics of their behavior, or it could be descriptive statistics of outcomes that happen in their life as a result of those audits having or that use of that model. So think.
Got it. Great.
Yeah.
Fantastic. So the latter sounds like something that's a very good fit for differential privacy.
Yep.
That is kind of statistical analysis of a data set, in this case, the user logs of users who've been affected by AI models, decisions have been taken, and you want to do statistical analysis of this, and it's sensitive data that you don't want to disclose really about specific individuals, but to know whether the model on the whole is producing, for example, fair outcomes according to some metric. That seems like a very good fit for differential privacy. For the first one, I'm having a little bit harder time thinking of exactly how differential privacy would play a role. And it sounds like maybe more of a context where other privacy enhancing technologies on their own would be the maybe the right tool for doing some kind of audit where you want to check some properties of the model, but the AI provider doesn't want to actually release the model as a whole.
Yeah, and I think that is the right framing. And the only other additional link that is probably the area of active research more than anything else. People are worried about if you consume enough outputs from a model that you could then use that to retrain a new version of the model, which has a very close tie to reconstruction attacks if you're reconstructing some aspect of the model. But it's not clear to me that there's a direct theoretical tie between, the performance of the model you could reconstruct versus the epsilon budget that you've spent receiving things. So that probably interesting research to be done there, to be honest. But,
yes, it does sound like a very interesting research question.
But actually, the former one you mentioned is such a close tie. I guess I should give a shameless plug. Last year, we facilitated some AI audits at LinkedIn and Dailymotion, and actively researchers used OpenDP specifically to protect user logs during the course of those audits. So
fantastic.
It was a very successful tool and seemed to be liked by all parties involved, which was great.
Great.
Let's see. We've got another question that just came in from Jacob. So Jacob asks, "What is your perspective on the impact of quantum on current privacy-preserving technologies? Do you foresee these technologies being adapted to post-quantum environments in the near future?"
Great. So differential privacy itself, fortunately, doesn't really have vulnerabilities to quantum computation because it provides kind of an information theoretic guarantee that's not relying on the assumption of hard computational problems like the hardness of factoring large integers or the discrete logarithm problem, which are problems that if people can build scalable quantum computers would no longer be hard problems. And that's why there's a need to replace encryption technologies and so on, or a push to replace them with ones that are post-quantum secure. Now, when you use, though, in production, almost in many settings in which you would deploy differential privacy, it would need to be used in conjunction with tools from cryptography, even just at a minimum for access control to the data set, for keeping the data encrypted, for pseudorandom number generation that's then used to generate the noise in your differentially private algorithms. And so it would be important that all of those other components are post-quantum secure if you're worried about an attacker who actually has a scalable quantum computer in hand.
Oh, that's a very nice piece of nuance. And I assume OpenDP will be chasing these post-quantum tools as well as each of them come out.
Yeah, I mean, so far, the main cryptographic technology that we use in the core OpenDP is just pseudorandom number generation, where it's conjectured, at least, that the standard ways we do pseudorandom number generation, for example, using AES, the Advanced Encryption Standard, block cipher, those are all believed to be post-quantum secure, so there's not really a risk there. They're not based on number theoretic tools. It's probably more in the end-to-end systems that may have some public key infrastructure associated with it for user authentication and so on, or other key exchange, the kind of web protocols that one would be worried about post-quantum secure. So it hasn't been a main focus for us because we're kind of relying on other libraries for providing those functionalities at the moment, and those will get updated when the bigger shift happens to post-quantum secure.
Got it. Very cool. And I apologize to folks submitting questions. We might not be able to get to all of them by the time, but I'm trying to pick out ones that are most representative of the group. Here's one that's kind of a back to basics question. So what are the best topics to do research in differential privacy? So kind of, I guess, interesting open problems, I guess, is sort of the maybe a good lead here.
Yeah, that's a great question. That I think I would go back first to the point I made earlier. The field has become vast. There are many entry points, and you should look for problems that again relate to your own individual interests and expertise. I don't necessarily recommend saying, okay, this is the problems that the people who've been working in this field for 25 years say are the open problems.
The best. Yeah.
That said, so I mentioned a few that are related to my own interests. Like we still don't understand the best way to do basic statistics like linear regression, logistic regression with differential privacy from a theoretical point of view, or even empirically. I don't know that we have necessarily the go-to method. And then I mentioned some problems with composition, but those are very, those are idiosyncratic to my interests and the problems that I've encountered. And I would suggest that you again find things that are close to your interests and toolkit.
That's great advice. I love that. Here's one that's I feel like we get this question a lot, and I'll be very curious to hear your answer myself. How well does DP align with privacy standards like GDPR, CCPA, and how can it evolve to meet future regulations?
Great. It's been a really sort of fascinating process how over the Privacy Tools project that I mentioned and these kind of interactions with legal scholars to be looking at the relationship between kind of what we're doing in differential privacy and legal requirements for privacy protection. I do think that over time things have becoming more aligned. I mean, in many respects, GDPR, the language used there was one that's closer to being able to make ties to kind of what differential privacy is protecting than, for example, the HIPAA privacy law, back from I think the 1990s. That said, it's still a very different language, and there's been a lot of really interesting work. I would recommend works by people like Kobe Nissim, Aloni Cohen, Alexandra Wood, and others that have been really doing a sort of rigorous combined legal technical analysis of the regulations and their relation to privacy protection. And they did a very nice study around GDPR, which has a notion of singling out, and made a strong argument that differential privacy satisfies the requirement to not be able to single out any individual.
Cool. I love that. That's brilliant. Maybe if you have any resources we should share, we'll share them on OpenMined Slack and socials as well, on that question. All right, I think maybe we can sneak time for one more real quick, and then we can be done. So will DP remain the standard for privacy preserving techniques in the future, or are alternative approaches emerging? Is it worth specializing in differential privacy?
Great. It's a commonly asked question. People often wonder, especially because there is this difficult trade-off between privacy and utility that is in some sense inherent, but is exposed by differential privacy. And people do have hope that maybe if we have some different definition of privacy, we can have some better privacy utility trade-off. That maybe there are cases in which differential privacy is too pessimistic, thinks too adversarially, so on. There is a possibility that something like that would be discovered, but so people have given that a lot of thought over the years, and the efforts to do so have really gotten stuck in producing something that's really workable and usable and has the various features like compositionality features that differential privacy has that allow us to, again, kind of reason about simple components and build complex things out of them. And so from that perspective, it looks like differential privacy, with its many variants, like I mentioned, things in the spirit of differential privacy are kind of here to stay, as far as we can tell. But even if something new comes along, my expectation is that the way of thinking about data privacy that differential privacy has given us will continue past, will continue far into the future. And so I don't think you should worry about your time being wasted investing in developing the understanding that differential privacy is giving you, because those insights about what it means to protect privacy and the pitfalls there are really kind of independent of the specific definition of privacy, and it's more about the way of thinking about data privacy.
Brilliant. Man, what a wonderful place to close. Tudor.
So I think we can wrap it here. Thank you again, Salil, for joining us today. It was a wonderful talk and a wonderful conversation. And we conclude the first episode of our series with leaders in privacy enhancing technologies. Thank you again, and looking forward to see what you and the OpenDP community will continue to deliver for differential privacy.
Thank you all.